All right, so we are looking at section 1.5, which is on exponential and logarithmic functions. So a couple of things that we're going to go over in this section is to identify the form of an exponential function, explain the difference between the graphs x to the b and b to the x, recognize the significance of the number e, identify the form of a logarithmic function, explain the relationship between exponential and logarithmic functions, and then describe how to calculate a logarithm to a different base. The hyperbolic functions we won't go into right now, so we'll skip that last part. Okay, so just kind of reading along, in this section we will examine exponential and logarithmic functions. We will use the properties of these functions to solve equations involving exponential or logarithmic terms, and we study the meaning of and importance of the number e. We also define hyperbolic and inverse hyperbolic functions, which involve combinations of exponential and logarithmic functions. All right. Okay, so let's start with the exponential functions. And again, this is kind of a review from pre-calculus, so we'll go quickly through it to try not to make this video as long as the last one. So exponential functions arise in many applications. One common example is population growth. For example, if a population starts with p sub 0 or p naught, since it's called individuals, and then grows at an annual rate of 2%, its population after 1 year is, so how would we represent that new population after 1 year? P of 1, the population after 1 year, it should be equal to the initial population plus 2% of the initial population, because it's growing. So that's why we have a plus sign there. It's growing by 2% of the original. And so if you notice that both of these terms have p naught in them, we can factor out the p naught. And then notice that this has a coefficient of 1. So we end up with 1 plus 2%. And so, of course, it kind of makes sense that you should get 102% of p naught, right? If it grows by 2%, you of course start, the initial population will count as 100% of the population that it started with. And so after 1 year, you have 102% of the original population. If you go, well, what about the population after 2 years? Well, after 2 years, that is going to be the population from after the first year. And then it's going to grow 2% again. Each year it grows 2%, but it's going to grow at 2% of the population after the first year. So again, these two terms have a P1 in them. So we factor out that P1, and so we get P1 times 102%. And remember that P1 from before was equal to P naught times 1.02. So if we kind of plug this in right there, this is P naught times 1.02. And then we have another factor of 1.02. So we can write this as, P naught times 1.02 squared. And so we see, okay, P of 1 was equal to P naught times 1.02 to the 1. P of 2 is equal to P naught times 1.02 to the 2. And so P of t in general, we see on the next line, the population after t years is going to be equal to, and of course it should make sense that the population after some number of years is somehow related to the initial population, and then somehow related to the growth rate, 1.02 raised to the t. And of course the number of years should matter as well. So this is an exponential function. More generally, any function of the form, we're going to extend this to just, be anything of this form. A function of x, f of x, equals b raised to the x. So the exponent is, or the variable is in the exponent. And we require that b be a positive number and b not be equal to 1. So this is an exponential function with the base of b and an exponent of x. Exponential functions have constant bases and variable exponents. Note that the function of the form f of x equals x to the b for some constant b, this would be like, the difference here is the exponential f of x equals, x, or let me do the exponential first. That would be 2 to the x, and then the f of x equals x squared. You know what this is. This is a parabola here, and this is an exponential function. Okay, so in this form here, f of x equals x to the b, where the exponent is constant, this is not an exponential function, but something called a power function. To see the difference between an exponential function and a power function, we compare the functions y equals x squared and y equals 2 to the x, the ones I've written down. In table 1.10, we see that both 2 to the x and x squared approach infinity as x approaches infinity. It makes sense that as x gets bigger and bigger numbers, when you square them, they get even larger. But when you raise to bigger and bigger numbers, that gets larger as well. So you see here, let me go ahead and highlight. In yellow, I will highlight the exponential. Notice it starts off small for small values of x, and then it gets pretty large. It goes all the way up to 64 here for a value x equal to 6. What does the x squared do? Well, x squared is, it's 9. It starts getting smaller. But then as the numbers, the inputs get positive and bigger, then we see that the values are increasing, and we get a value there of 36 when x is equal to 6. Notice that for the value of x equals 6, the exponential is actually larger, right? This one is larger here. Maybe if you were to go, back over here somewhere where x is equal to -2, the x squared term is actually bigger. But it turns out that exponentials grow larger and larger faster. As you go further along, the exponential will actually increase a lot faster than, the x squared term. Okay, so it does say eventually, however, 2 to the x becomes larger than x squared and grows more rapidly as x approaches infinity. In the opposite direction, as x goes to -infinity, x squared goes to infinity. Okay, as we can see, if you go in this direction for x squared, you see the x squared values. These are actually, from right to left, these are getting bigger in that direction. But if you look at the exponential, in this direction, they're actually getting smaller, right? So it says, whereas 2 to the x goes to 0, the line y equals 0 turns out to be a horizontal asymptote for y equals 2 to the x. Okay, so it approaches 0 to the left as a horizontal asymptote, and then it actually goes to infinity as x goes to positive infinity. So here are the graphs. You can see those tables essentially in these graphs. Notice that 2 to the x is, it's small here. It has small values. I'm drawing it in red down here. It has small values, but notice how fast it shoots up and then eventually overtakes. It is now rising faster. It has a larger value. Let's say for this x value here, x squared would be down here, but 2 to the x is way up there already. It rises way faster. Okay, so evaluating exponential functions. Let's just quickly talk about how to do that. Recall the properties of exponents. If x is a positive integer, then we define b raised to the x as just, the base raised to the x. So the base is going to be multiplied x times. So there would be x factors of b. If x is a negative integer, well, then x is equal to negative some value y for some positive integer y. And so we define b to the x to be just, well, if x is equal to negative y, then we can write b to the x as b to the negative y. And then that negative in the exponent can be used to write this as the reciprocal of b to the y, or 1 over b to the y. Also, it's commonly defined that b to the 0 is defined to be 1. Okay. If x is a rational number, so if x is a rational number, meaning like a fraction, then, x would be equal to p over q for some integers, p and q. So it says where p and q are integers. And then we know what that means. If b to the x is equal to, that would mean that b to the x is equal to b to the p over q. And then the p is treated as an exponent. The q is treated as a root. So it'd be the qth root of b to the p. And then they give an example here, very nice. What is 9 to the 3 halves? 9 to the 3 halves, so that would be the square root of 9 to the 3rd. And you can figure out what that is. It looks like they're saying it is 27. And yeah, you can actually kind of switch these things around. You can say the square root of 9 to the 3rd. In this case, the square root of 9 we know is 3. 3 to the 3rd is 27. So just to verify. However, how is b to the x? We kind of get into a bit of a more complicated question here. It says, how is b to the x defined if x is an irrational number? For example, what do we mean by 2 raised to the square root of 2? So it says this is too complex a question for us to fully answer right now. However, we can make an approximation, right? So we can approximate the square root of 2. I don't know what it is, and I don't have my calculator on hand here, but the square root of 2 is approximately 1.414, right? Roughly. So how do we calculate what the 2 to the square root of 2 is? Well, what we can do is we can list some rational numbers approaching the square root of 2, which is approximately 1.414 ... It continues in some, this is an irrational number. And then the values of 2 to the x for each of those rational numbers, x, are going to be presented in a table. So let's go ahead and take a look. So we let x be the value 1.4, and then we find 2 raised to that 1.4. And so we are going to approach, x is going to approach the square root of 2. So then the next approximation would be, okay, well, what if x is 1.41? Well, then we find 2 raised to the 1.41, and then 1.414, or 1.414, yeah, 2 raised to the 1.414. And we see that these numbers start to get closer and closer to a certain number. Okay, and as our approximation, or as our x gets closer and closer to the square root of 2, then this output value is going to get closer and closer to 2 raised to the square root of 2. So let's continue reading. It says, we claim that if we choose rational numbers, x, getting closer and closer to square root of 2, the values of 2 to the x will get closer and closer to some number L, and we define that number L to be 2 raised to the square root of 2. Okay, so for now, that will be our explanation for that. Bacterial growth. And since this is a review, I will skip this example. But if you want to see this example or kind of talk about it, feel free to visit me during my office hours, and we can go over it. Just don't want to make the videos too long. The last one was very long. Okay. So how do we graph exponential functions? We'll just give, again, this is a review, so we'll give some basic tips on graphing and some basic properties of exponential functions. So first, let's start with a green marker here, or a green highlighter. It says for any base b greater than 0, of course, b is not equal to 1. That's how the exponential was defined. The exponential function f of x equals b to the x is defined for all real numbers x. So that means that its domain is going to be all real numbers. So the domain of f of x equals b to the x is all real numbers. And then we're told right here that b to the x is actually, it turns out to be larger than 0 for any value of x. And so if b to the x is larger than 0, it turns out that the range is from 0 to infinity. And you can see that in these graphs below. It looks like these functions have domains from negative infinity to positive infinity. And their ranges, at least what we see so far, is from 0 to infinity. None of them seem to cross below the line y equals 0. They do follow it asymptotically at some point. Okay, so to graph b to the x, we note that for b greater than 1, so we're going to split this up into two cases. When b is greater than 1, it turns out that when the base is greater than 1, like in this case here, f of x equals 2 to the x, it turns out that b to the x is increasing on the entire interval from negative infinity to positive infinity, and b to the x goes to infinity as x goes to infinity, whereas b to the x goes to 0 as x goes to infinity. So what is it saying? It's saying this here. I will highlight it here. And maybe I should underline it in red to color coordinate here. So this function is increasing, and you can see that in the function right there. It is increasing. Okay, so that's from left to right, the function is increasing. Now, b to the x goes to infinity as x goes to infinity. That basically says at the end behavior, essentially, it's shooting off to infinity. As we go further and further to the right, the function goes up. Whereas b to the x goes to 0 as x goes to negative infinity. So if you're going to negative infinity in terms of x, the function actually gets closer and closer to y equals 0. We can see that on the graph. On the other hand, if b, the base, is a fraction between, or some number between 0 and 1, like let's say 1/2 to the x, then what do we have for this function? It turns out that this function, f of x equals b to the x, is decreasing on the interval from negative infinity to positive infinity. You can see that there. From left to right, it's falling from left to right. That's decreasing. Then b to the x approaches 0 as x goes to infinity. We can see that right here. I'll draw it in purple. Yeah, it's approaching 0 as x goes to positive infinity, whereas b to the x goes to infinity. So this function goes to infinity as x goes to negative infinity. So as we go further to the left on that function, it is going up to infinity. Okay, visit this site, and you can actually click on it there and open in Safari if you want to more explanation of the graphs of exponential functions. So that's kind of cool. Okay, so note that exponential functions satisfy the general laws of exponents. And to remind you of these laws, we state them as rules. So again, this is review. You've probably seen these before. So for any values, any constants, a greater than 0 and b greater than 0, and all values x and y, whenever you multiply two exponentials, b to the x times b to the y, then you can just add the exponents. This is b to the x plus y. Similarly, for division, b to the x divided by b to the y, that's b to the x minus y. You can subtract the exponents. B to the x, if you have an exponential and you raise it to another exponent, then you can just multiply those two exponents together. That's b to the x times y. Exponents essentially distribute, if you want to call it like that, exponents distribute over multiplication. So if you have a multiplication like a times b, and that product is raised to the x, then we can raise each of the factors to the x. And then same thing over division. That's number 5. So using the laws of exponents, again, this is one that you've probably seen before. You can see me during office hours if you would like to go over this problem. These are not too hard to follow if you just read them. All right, the number e. So a special type of exponential function appears frequently in real-world applications. To describe it, consider the following example of exponential growth, which arises from compounding interest in a savings account. Suppose a person invests P dollars in a savings account with an annual interest rate R, compounded annually. the amount of money after 1 year is, and so this is kind of similar to that population example that we saw earlier. So if you put in P dollars and you are getting an interest rate of R, so let's say like 5% or something like that every year, if this is compounded annually, then how much money will you have after 1 year? The amount after 1 year is going to be the initial amount that you invested, that's P for principal, plus what are we going to add to that? Well, the interest rate times your initial amount, so 5%, let's say, of your initial amount. Both of these terms have P in them, and so we can factor out the P, and we'd be left with a factor of 1 plus R. So we have P times 1 plus R. How much money is in there after 2 years? After 2 years, well, we would definitely still have the amount of money that we had after 1 year. Plus, we would add to that, then we would find like 5% or whatever the interest rate is of the amount that we had after 1 year. We would apply the interest rate to the amount that we have after 1 year, and then we'd add that on to the amount that we have. Okay, so A1 is a common factor of both of these two terms. So we factor out A1. What would we get? I'm going to write it here. A1, they kind of skipped a step. A1 times 1 plus R. But wait a minute. A1 from the previous line over here, A1 is equal to P times 1 plus R. So my A1, I'm going to write it as P times 1 plus R times 1 plus R. And what do we have? That is P times 1 plus R squared, which is exactly what's written here. Okay. So then we can see in general, after T years, the amount in that account is going to be A of T equals the principal times 1 plus R raised to the T. Okay. Where is that E showing up? Oh, it's coming here pretty soon. If the money is compounded 2 times per year, the amount of money after half a year is, the amount of money after half of a year is going to be equal to the initial amount of money, P. And then, well, we're not going to apply the interest rate since it's only been half a year, but we're compounding 2 times per year now. So we're going to apply half of the interest rate after half of a year. And so you'll get half of the interest rate applied to your principal amount, and that will be added on to the initial amount P. And again, we have a common factor of P. We can factor out that P, and our other factor ends up being 1 plus R over 2. Now, how much money is in there after 1 year? Well, after 1 year, there's going to be another half year. So we're going to have the amount that was in there after half of a year, which we just found an expression for in the previous line, plus then we're going to apply the half of the interest rate again. And that is going to be applied to the amount that we had after the first half year. Now, let's go ahead and do some substitution here. A of 1/2, that is from before, that is equal to P times 1 plus R over 2. So that's why that's there. And then we have R over 2 times A of 1/2. So R over 2 times the exact same thing as the first term there. And if you factor out, what can we factor out there? Let's see here. Both of those terms have a 1 plus R. Yeah, both of those terms have a P times 1 plus R. Notice we can highlight it here. P times 1 plus R over 2. P times 1 plus R over 2. If you factor that out, it's a little bit of algebra here. P times 1 plus R over 2. If you factored it out, you would end up getting, right, because there's a coefficient of 1 here, you would end up getting 1 plus R over 2. And notice you would get P times 1 plus R over 2 squared. Okay, so after 1 year, you have this much money in your account. So after t years, we could continue this and we could keep doing half years, but we can generalize this now. And it turns out that after t years, the amount of money in the account is going to be A of t is equal to P times 1 plus R over 2 raised to the 2t. Now let's generalize even further, more generally. If the money is compounded n times per year, not just 2 times per year, but n times per year, the amount of money in the account after t years is given by the function A of t is equal to, and you'll recognize this as the previous function, but instead of n equals 2, instead of the value 2, we have an n there. So what happens as n approaches infinity? To answer this question, we're going to take a look at 1 plus r over n raised to the nt, and we're going to let, it says, m equal n over r, okay? If we let m equal n over r, then notice that if we flip the right-hand side, r over n, this is going to be equal to 1 over m. And then if we also solve this equation here for r if we solve this equation for n by multiplying by r, we are going to get the equation that n is equal to m times r. Right, so a little bit of algebra here, and then we'll see that all of these statements are used going forward here. So let's go back to this expression here, which is part of our function there. So 1 plus r over n, we said that is 1 over m. And then nt, well, n we solved to be mr. So this is going to be, instead of nt, mrt. And that's how they got what they have here. And so we want to look at this function here. We can actually look at the behavior of 1 plus 1 over m raised to the m, and then we'll raise that to the rt, right? And notice that there was a p in front of all this. I kind of left it out for a moment, but there was a p, and this is exactly equivalent to what we have here with the substitution that m is equal to n over r. Okay, so we are interested in what is happening to this highlighted portion. And so we're going to examine the behavior of this highlighted portion as m goes to infinity. And then using the table of values, we can see that m is chosen to be 10, 100, 1,000, and so on, getting infinitely large essentially. And does the expression that is highlighted, 1 plus 1 over m raised to the m, does that get infinitely large as well? And it turns out no. You can take a look at these values here, 2.59, 2.70, 2.71, 2.718, 2.7182, and so on. It turns out that this value, the value as m goes to infinity of this expression here ends up being a value between 2.7 and 2.8, right? Because this is 2.7. It might be increasing a little bit from before, but it's somewhere between 2.7 and 2.8. It doesn't look like it's going to be larger than 2.8. And it says, looking at this table, it appears that the expression is approaching a number between 2.7 and 2.8 as m approaches infinity. In fact, 1 plus 1 over m raised to the m does approach some number as m approaches infinity. And this is the number that we call e. To 6 decimal places of accuracy, e is approximately 2.71828. So a little bit of a history here. The letter e was first introduced was first used to represent this number by Swiss mathematician Leonhard Euler during the 1720s. Although Euler did not discover the number, he showed many important connections between E and logarithmic functions. We still use the notation E today in honor of Euler's work because it appears in many areas of mathematics and because we can use it in many practical applications. Okay, so returning to our savings account example, we can conclude that if a person P puts P dollars in an account at an annual interest rate R, compounded continuously, so if the number of compoundings n goes to infinity, then the function becomes a of t equals p e to the rt. And so, right, remember earlier, this becomes p, and we just said p times, we said that the highlighted portion becomes closer and closer to e. So this is how we get our equation, p times e to the rt. This function may be familiar. You may have seen it in pre-calculus before. Since functions involving base e arise often in applications, we call the function f of x equals e to the x the natural exponential function. It's definitely an exponential function because it's some base, some constant base raised to the x. Not only is this function interesting because of the definition of the number e, it's kind of defined in a funny way, but also as discussed next, its graph has an important property. Okay, and so what is this property? Since e is greater than 1, we know that e to the x is increasing on the interval from negative infinity to positive infinity. In figure 1.45, we show a graph of f of x equals e to the x, along with a tangent line to the graph at x equals 0. We give a precise definition of tangent line in the next chapter, but informally, we say that a tangent line to a graph of f at x equals a is a line that passes through the point a f of a. So the function f of x equals e to the x, we can evaluate f at 0, and that is e to the 0, which is equal to 1. So we know that the point 0, 1 is on the graph f, and 0, 1 is this point here. I'll put a big dot there. And that is 0, 1. And so the tangent line at x equals 0 is a line that passes through the point, in this case 0, 1, and has the same slope as f at that point. Now, we haven't really talked about what the slope of an exponential function is. Usually we just talk about slopes of lines, but in this class, we're going to discuss slopes of other functions as well. The function f of x equals e to the x is the only exponential function, b to the x, with a tangent line at x equals 0 that has a slope of 1. Okay, and so you can see the slope of 1 here in this picture. As we see later in the text, having this property makes the natural exponential function the most simple exponential function to use in many instances. And you will see this function come up a lot later in this text. All right. Compounding interest. Okay, this is a very, again, review problem, so we'll skip it. We're just trying to get a refresher. Okay, so logarithmic functions. This is the last section here that we're going to cover, I believe, in this section. So, or maybe not, but we'll see. Using our understanding of exponential functions, we can discuss their inverses, right? This was what the last section was about. It was about inverses. And so exponential functions have inverses. Those inverses are called logarithmic functions. These come in handy when we need to consider any phenomenon that varies over a wide range of values, such as, whoa, sorry about that. My pencil got away from me. Such as pH values in chemistry or decibels in sound levels. There's an example at the end of this later on in this section. Okay, so the exponential function f of x equals b to the x. You remember the graph of it. It looks something like this. It is a definitely one-to-one function. Right, we talked about that in the last section. Its domain is all real numbers. Range was from 0 to infinity. So because it's one-to-one, it must have an inverse function. or it has an inverse function. We call that inverse function the logarithmic function with base b. Okay. And for any b greater than 0 and not equal to 1, the logarithmic function with base b, denoted, it has the notation log with the subscript of b, read log base b. It's going to have a domain. We should know what the domain is going to be. The domain is going to be the range of the exponential, which is 0 to infinity. And the range of the logarithm is going to be the domain of the exponential, negative infinity to positive infinity. And I'll just sketch a graph right here. It's going to look something like this. And you can see its domain and range there. Of course, we know from the previous section that these two graphs must be symmetric about the line y equals x. Okay, and the logarithm satisfies, it is very important that we memorize, this to give us an easier time in our class. And this says that a logarithm, log base b of x equal to y, is equivalent to, I use this double arrow for if and only if, that means is equivalent to b to the y equals x. So whenever we have a logarithm written, a logarithmic equation written in this form, we can rewrite it as an exponential equation. And this is part of the definition of the logarithm. Okay, so how do we, use these logarithms? Okay, well, let's just go over a couple examples here. They give us 3 of them. The log base 2 of 8. What does this mean? Log base 2 of 8. This essentially means 2, I'm going to put equals x here. Let's just say we don't know what the log base 2 of 8 is. So we're going to say the log base 2 of 8 is equal to x. Using the equivalence that was given on the previous page there, we can rewrite this logarithmic statement, log base 2 of 8 equals x. We can write this as 2 to the x equals 8. And essentially what we're asking here is 2 raised to what exponent is 8? And we all know that that exponent is 3. 2 to the third is 8. So that means that the log base 2 of 8 is 3. Okay, so logarithmic equations are really asking things about exponents. So the second example, log base 10 of 1 over 100. Basically, we're asking what exponent do we need to put on 10 to get 1 over 100? And yeah, I'll just leave it as 1 over 100. Since it's a reciprocal, we know it's going to have to be a negative exponent, and then it's 10 raised to the second power gets us 100. So the negative second will be the answer. And so the exponent that you need to put on 10 to get 1 over 100 is -2. The answer is -2. Finally, our last one here. What is the log base b of 1? Let's suppose that we don't know what this is, so I'm going to call it x again. And so we'll use the equivalence that is listed, that's given up here. This is very important. We will write it equivalently as b raised to the x equal to 1. B raised to what exponent is equal to 1? Well, we know that b to the 0 is 1. So this is equivalent to, if we rewrite this in logarithmic form, this says that the log base b of 1 is 0. Okay. Now, furthermore, since y equals log base b of x and y equals b to the x are inverse functions, we know that when you apply an inverse function to another function, in a lot of cases, they cancel out, right? So yeah, if you wrote this as f of x equals the log base b of x, and f inverse of x is equal to b to the x, then essentially what we're saying here is that f of f inverse of x is equal to x. And unlike the trigonometric functions, which we had to restrict the domains on, there are no restrictions on the domains here. So this is true for any value of x. Okay, and then similarly, so basically, if you have an exponential, like b to the x, and you apply its inverse, you apply to it the log base b of x, essentially the log base b and the b exponential, they cancel each other out and you just get x. Okay. And then similarly, if you have b an exponential, but what it's raised to is the log base b of x, then this is a similar thing here. The logarithm and the exponential are going to cancel each other out, and we're just going to get x. The most commonly used logarithmic function is the log base e, right? So let's highlight it here, the log base e. We saw e earlier, and it was an exponential function that was very important. So its inverse is the log base e, and it is very important as well. Since this function uses the natural e as its base, it is called the natural logarithm. Here we use the notation ln of x. So ln of x, or ln x, means the log base b, log base e of x. So for example, the natural log of e is really the log base e of e, but we said that those are inverse functions, and so they essentially cancel out and you get 1. Similarly, the natural log of e to the third, that's the log base e of e to the third, and according to what we said earlier here in green up above, this should just be equal to the exponent, which is 3, and that's what we get. Okay. Now, the natural log of 1, turns out that the log with any base of 1, we just said this earlier up above, is equal to 0. So there's no surprise that the log base e of 1 is also equal to 0. We just said this up above for any base b greater than 0. So of course it should apply to e. Since the functions f of x equals e to the x, and so f of x equals e to the x and g of x equals natural log of x are inverses of each other, well, it makes sense that f of g of x, which is f evaluated at g, so e raised to the natural log of x, since these are inverse functions of each other, this should be equal to x. That's exactly what this statement is saying here. And then in a different color, we'll say, well, what about g of f of x? Remember here, we are saying that f and g are inverses of each other. So when you apply two inverse functions, inverse functions to one another, then they should cancel out and you should get x. So g of f of x, that is the natural log evaluated at e to the x. And we actually just showed, I'll point it up here, we're essentially just saying the same thing, but the base is e here. So nothing new, actually. We just said this. This is equal to x. Okay, they're just saying it again in the textbook for some reason. And their graphs are symmetric about the line y equals x. Yeah, of course, that should be true because we said that from the previous section. All right, so nothing special there. Okay, in general, for any base b greater than 0, b not equal to 1, the function g of x equals log base b of x is symmetric about the line y equals x with the function f of x equals b to the x. Yes, of course it is. It should be. That's what we said in section 1.4. All right. Okay, so b to the x, let's see. Using this fact and the graphs of the exponential functions, we graph log base b for several values of b greater than 1. When b is greater than 1, we said earlier that the exponential is going to be increasing. So here is an exponential. Let's suppose this is f of x equals 2 to the x. Well, then that means that the logarithm, its inverse, which is going to be f inverse of x, equals log base 2 of x. That means it's going to be increasing as well. So before we show that, oh, there we go. And they give 3 examples. Okay, I only gave 1. But of course, if you look at more exponential functions, you can graph another one. Okay, well then, you can graph more logarithmic functions. Okay, very good. Before solving some equations involving exponential and logarithmic functions, let's review the basic properties of logarithms. Okay, so what do the properties of logarithms say? And these are kind of similar to the exponential properties. They actually rely on them. So if a, b, and c are larger than 0 and b is not equal to 1 and r is any real number, then the product property, the log base b of ac is equal to the log base b of a plus the log base b of c. So you can decompose basically this product here. The log of a product becomes a sum of logs. Okay. The quotient rule is the quotient property is very similar. The log of a quotient is the difference of 2 logs. I won't rewrite that one. Now the power property is very, very powerful. So we'll write it again. The log base b of, let's say, x to the r, right? Doesn't really matter. Basically what this one says is if you take the log of an exponential like x to the r, we can bring down that exponent. This is going to be equal to, we can write the r on the outside of the log before the log, multiplying that log, it'd be equal to r times the log base b of x. No longer does it have the exponent of r, it is now in the front. And these properties can be proven. We're not going to prove them. Maybe they were proved in your previous class. That's not important for us right now. Okay, so solve each of the following equations for x. Okay, so how do we do this? 5 to the x equals 2. There's a couple ways to do this, and I'll look at what they do here. They apply the natural log to both sides. Now, if we apply the logarithm to an exponential, that means that we can bring that exponent out to the front. And so this means this is x times the natural log of 5 equals the natural log of 2. And then we have, x times the natural log of 5. We have 2 factors here. We can divide by the natural log of 5 on both sides, and we are done. X is equal to the natural log of 2 divided by the natural log of 5. Now, I was thinking of a different way to solve this, so let me solve it one more way, just because that was my initial thought. 5 to the x equals 2. I was actually going to use the equivalent statement that we were given for logarithms and exponentials a little while ago. And that was that basically b to the y was equal to x was equivalent to log base b of x equal to y. Now, do we have to use this? We're actually going to see later in this section that this is okay to use. So I'll use it. Why not? And then it's a good solution as well. It's actually quicker. Yeah, so this is equivalent to, if we use that, this is equivalent to log base, the base of the logarithm is the base of the exponential, log base 5, of whatever's on the opposite side of the equal sign, which is 2, which is equal to x. And we're done. It only took one step. So I'm just going to rewrite this here so I can write with the x on the left-hand side, because that's what I prefer, but you don't actually need this step. X is equal to the log base 5 of 2. And we're going to see in a little while that actually the log base 5 of 2 is equal to the natural log of 2 divided by the natural log of 5. So this is equivalent to the answer that we got in the other solution. All right, so 2 solutions there, or 2 ways to get the solution. Nice. let's take a look at the next one. The next one is e to the x plus 6 over e to the x. We have an e to the negative x, which we can write as a fraction, 1 over e to the x. And so it has a coefficient of 6. So how do we do this one? Well, let's get rid of fractions because we don't want fractions. E to the x, we can multiply by the lowest common denominator. And this is going to give us what? We multiply here. E to the x times e to the x is e to the 2x. Here we multiply e to the x by 6 over e to the x. The e to the x is canceled, leaving us with just the 6. And then 5 times e to the x is 5 e to the x. Now, this is kind of a cool little problem here. We're going to subtract 5 e to the x on both sides. And what do we get? We end up getting e to the 2x minus 5 e to the x plus 6 equals 0. And what do we do with this? You might recognize this here. We can use the properties of exponents that we showed earlier to write this as e to the x squared minus 5 e to the x plus 6 equals 0. And I'm going to make a substitution here. I'm going to let y be equal to e to the x, just to make this look a little bit cleaner. If y replaces e to the x, then we have y squared minus 5y plus 6 equals 0. And notice that this is a quadratic equation in terms of y. And so we can factor this. We find two numbers that multiply to 6 that also add up to -5. That would be -3 and -2. Am I right? They multiply to +6, add up to -5, yes. And so we split up our middle term. Our middle term is going to become y squared minus 3y minus 2y plus 6 equals 0. Here we're just factoring now, right? So we have, if we factor a common factor of y from these two, y minus 3, and we can factor out a -2 from the second set of terms. If we factor out a -2, we end up with y minus 3. And notice we have a common factor again of y minus 3 in both of these terms. And so this becomes y minus 3. If we factor it out, and we're left with y minus 2, which is just a remainder of after you factor out the y minus 3. Okay, and then making our substitution back in, right? Remember that y was equal to e to the x. That was a substitution that we made just a moment ago. So we're going to substitute it back in. Y is e to the x. And so according to the zero product property, we can set both of these factors equal to 0. E to the x minus 3 equals 0. E to the x minus 2 equals 0. And so if we add 3 to both sides, or add 2 to both sides, then we have e to the x equals 3, or e to the x equals 2. We're almost done solving here. Notice I don't know if you could say they skipped a lot of steps here, but they definitely don't show all the details here. But the last step here is if we apply the natural logarithm to both sides of each of these equations, the natural log of e to the x, those two are inverse functions. So these essentially cancel and you get x equals the natural log of 3, or x equals the natural log of 2. Very nice. So those are our two solutions. Okay, so this should be kind of ringing the bell from before. And let's see here. Whew. Almost done here. How long is this one done? Okay, almost done. Let's just quickly show the examples here. Part A, we want to solve the natural log of 1 over x equals 4. Well, here we can use, and they're actually using it here in this solution that they go over, the equivalence statement, right? We said that the natural log of, this is actually the log base e of 1 over x equals 4. And don't forget our equivalence, that log base b of x equal to y this is equivalent to writing, anytime you see a logarithmic equation this simple here, you should maybe, it would be a good idea to somewhere on that paper, write it in its equivalent exponential form, b to the y equals x, right? Kind of just shift things around. So we're going to equivalently write that as the base of the logarithm raised to whatever's on the other side, which is 4, equals 1 over x. Okay, and then we can solve this for x by, we can solve this for x by, well, there's actually two ways. You know what, the easiest way is just, if we have two things equal to each other like this, we can just take the reciprocal of the left-hand side, which is x over 1, or the right-hand side is x over 1. Then we take the reciprocal of the left-hand side. That's a nice little trick. And so x is equal to 1 over e to the 4. Bam. Okay, very nice. Let's move that aside. Next, log base 10 of the square root of x, which I'll write as x to the 1/2, plus the log base 10 of x equals 2. Now, I don't know how they solve this. I guess I could look really quick. Yeah, there we go. Okay, so yeah, their solution is pretty nice. So let's do theirs. Yes. So what do they use? They use the property from before that the log base b of, I think it was a, let's say a plus the log base b of c is equal to the log base b of ac, right? You can go back and check to make sure that basically it started this way as a product. You can split it up into a sum of logarithms. But here I've written it backwards because you can also take a sum of logarithms and write them as the log of a product. So this left-hand side is going to be equal to log base 10 of x to the 1/2 times x. Now x, it's raised to the first power, and that 1 we can write it as 2 over 2 because to get a common denominator. And the reason that we do that is because we know that when we multiply exponential expressions with same base, we can add the exponents. So this is going to be x to the 3/2 equals 2. But then wait a minute, didn't we say earlier that if we take the log of an exponential expression, we can bring that exponent out to the front? Yes, we did. So we bring that exponent out to the front. And so this is what we have. We can then multiply by 2/3 to cancel out those fractions on the left-hand side. And so we have the log base 10 of x equals 4 over 3. And then what? We can actually use this same equivalent statement again to rewrite this in an exponential form. So let's go ahead and do that. That'll be good. So this is going to be the base of the logarithm raised to whatever's on the other side, 4/3 equals the argument of the logarithm. So x is equal to 10 raised to the 4/3 is our answer. I don't know if they approximate that. I don't have my calculator, like I said. So the answer is, 10 to the 4/3. Now, yeah, that's true. You can write this as 10 to the 4/3 is 3/3 plus 1/3. They're just simplifying it a little bit. And so this can be written as 10 to the 3/3 times 10 to the 1/3. And 10 to the 3/3 is 10 to the 1, or just 10. And then 10 to the 1/3 is the third root of 10. So yeah, some little bit of simplification there. Very nice. That's cool. Nice thing. All right. Last one here, part C. And I'm just writing these here. You can take a look at their solutions. Maybe I can look at it there, but the natural log of 2x minus 3 times the natural log of x squared. The one thing I really like about logarithms is that there's so many ways to do these problems. So one thing we could do here is, let's see here, the natural log of 2x. We said we can use that power rule. So we can move this 3 back into the exponent, right? Kind of use it backwards. This is minus the natural log of x squared raised to the 3rd power equals 0. And so we have the natural log of 2x minus the natural log of x to the sixth equals 0. Then we have a difference of two logarithms, which we can write as the quotient or the log, natural log, since we're using natural log here, natural log of 2x over x to the sixth. And I believe this, I'm doing it differently than how they did it in the textbook here. Maybe, no, actually they did that. This is the way they did it. The natural log of, if we cancel out an x, this is 2 over x to the fifth equals 0. Writing the natural log as the log base e of 2 over x to the fifth equals 0. We can then use that same equivalence, the one I keep saying is really important, to write the logarithm as an exponential. So this is e raised to the 0 equals 2 over x to the fifth. E to the 0 is just 1. 1 equals 2 over x to the fifth. And then we can, let's do what we did before, which we did the reciprocal of both sides. So let me go ahead and scoot some stuff over. And we have 1 equals 2 over x to the fifth. If we do the reciprocal of both sides, let me see here. Yeah. Then we have x to the fifth over 2 on the right-hand side. The reciprocal of 1 is still 1. Then we multiply by 2 on both sides. And so we get x to the fifth equals 2. And then finally, we can finish this off by doing the fifth root of both sides. X is equal to the fifth root of 2. Okay. And yeah, we can check for any extraneous solutions. Take this, plug it back into the original equation, see if it gives you an extraneous solution. I don't believe it does. Yeah. All right, and then finally, yes, the last part here. Whew. The last part, and we won't go over the whole thing, but it is, kind of important to go over this last part. It says, when evaluating a logarithmic function with a calculator, you may have noticed that the only options are log base 10 or log base, or it said, or log, that's log base 10, called the common logarithm. So log base 10 is the same thing as log, a lot of times called the common logarithm, or ln, which is the natural logarithm. A lot of times calculators only give those two options. However, exponential functions and logarithmic functions can be expressed in terms of any desired base b. So what do we do with log base 2? Well, it says if you need to use a calculator to evaluate an expression with a different base, you can apply the change of base formulas first. Using this change of base, we typically write a given exponential or logarithmic function in terms of the natural exponential and natural logarithmic functions. So there are two of these formulas. For the sake of time here, maybe we'll just go over one of them. So number 2 is probably the more famous of them. And basically it says that the log with any base a of some expression x, this can actually be written as the log with whatever base b that you choose of the original argument x divided by the log with the same base b of the original base a. Okay, and so we'll show an application of this. We actually did one earlier when I did the problem a little bit differently, when I said that the log base 5 of 2, so earlier I had the log base 5 of 2, and according to this formula here, this is equal to the log with any base. I'm going to choose the log base e of the argument, which is 2, over the log base e of the original base, which is 5. And we know that the log base e is actually the natural log. So the natural log of 2 over the natural log of 5. And wait a minute, that's what we said earlier. Okay, so just kind of going back and justifying what I did there. And here it actually gives it the natural log. If you let b be e, you can choose any base e. or any base b, but the more natural choices of b are e and the base 10, because those are the ones that are found on your calculator. Okay, the next section here proves both of these statements. They are pretty nice proofs, actually, so you can read through them and try to understand them. It's pretty nice proof, but we will skip the proof because I mean, you can just also just believe it. If you want some proof, come to my office hours and I will happily go through those proofs with you. Okay, so just a simple example. This is actually just as simple as the one that I showed here in purple. The log with the base of 3 of 7. And so basically the way I always remember it, log base 3 of 7 is, you can always use natural log for, log base e whenever you're doing the change of base. But this number, this number is usually higher, the argument, that one goes in the numerator. And the one that is lower, which is the base, it's written as a subscript, so it's lower down. That one goes as, in the denominator. So there you go. And now you can, maybe your calculator, most calculators will not do this. I don't have a calculator, at least not a handheld calculator, that will compute log base 3 of 7. Maybe you have a fancier calculator than I do. Some calculators will do it, but most will not. But if you rewrite it using the change of base formula in this form, basically any calculator, any scientific calculator will compute this now. Okay, so that's the usefulness of this change of base formula. All right, and for the sake of time, we will skip the Richter scale example. Pretty cool example, but we're already over an hour. So as I mentioned, hyperbolic functions we'll skip for now. And so we'll stop there. All right, there we go.